and discovered the second family of leptons. Heard this beautiful song, dance about the electron and its sisters, the muon sisters that join the family of leptons. And then, after the war, a lot of research money went into particle physics, and people started discovering particles all the time. When I came to Berkeley, experimentalists were discovering a new particle every other week. It was very exciting. And hundreds of new particles, which were similar to the proton and neutron, strongly interacting. They had this strong nuclear force, very similar to proton and neutron, and no one really understood how it worked at all. Which, for a young theorist like me, was great. Lesson number 6. In science, probably the same applies to every facet of life, business, whatever. Always look for the field or the question or the research direction which is the most challenging, where everyone else has failed, and where no one is working. Well, not no one is doing it. Don't just do the easy stuff. So I was particularly challenged by the fact that really there was no theoretical understanding. Now, and by that time, people were doing very high energy experiments of this type, colliding particles together to see what they were made out of, if anything. Now, by the end of the 1960s, it appeared mathematically that many of the patterns of these particles could be explained if you assume that protons and neutrons were made out of a kind of particle that no one had ever seen, a quark. Quarks have fractional electric charge, according to this mathematical description, but no one had ever seen any piece of matter with a fraction of the electric charge of the electron. Quarks were supposed to have charge 1/3 or 2/3 or minus 1/3 or minus 2/3. No one had ever seen that. So it seemed rather strange and somewhat a mathematical abstraction. So, according to this mathematics, the proton was made out of two kinds of quarks. We call them today flavors, up and down. And the proton was made out of two up quarks and a down quark. And if you flip the up quark to the down quark, you got the neutron. And other combinations of up-down quarks and other kinds of quarks that seem to be necessary, called originally strange quarks, since they were strange, could produce the pattern of the various particles that had been discovered. To make this at all sensible, one also had to do something else and assume that each of these quarks, the up, down, and strange quark, came in 3 different colors, 3 different kinds. There wasn't just one up quark, there were 3 up quarks, all the same except for the label, up, red, blue, green. We call them colors. The problem with this idea was that in these collisions, you would expect to make quarks and see them. The atom is made of electrons and nuclei, protons and neutrons, found in the nucleus. And if you hit an atom hard, the electrons come out. You ionize the atom. And the electrons can be collected and made to go into wires and power motors and are responsible for modern technology. So if you hit the proton, the nucleus hard, with another one, with enough energy to pull the quarks out of the nucleus and make the quarks run in wires and have quark electricity and quark motors and but no one had ever seen these quarks come out of all of these collisions. So you make the collisions with more energy. Maybe you need more energy. But over the years, the energy increased by a factor of 10, 100, now 10,000. No one has ever produced a quark. So most people said, okay, there are no quarks. That's just a mathematical abstraction. Okay. The turning point for me was an experiment that was done at Stanford, the Stanford Linear Accelerator, where electrons were scattered off protons. So an electron, which is a simple point-like particle, scattered off a proton, again, very much in the spirit of Ernest Rutherford, to try to understand what happens inside the proton. And these experiments discovered a phenomena which could be interpreted by some of us. Some people said, that's silly. But some people said, those experiments suggest that inside the proton, if you look at the proton at short distances, the same way Rutherford did, you discover that the proton looks like you have three quarks moving around. Just moving around freely inside the proton. This discovery, some years later, was awarded the Nobel Prize for the discovery of quarks. And many people, many of us, regarded this as a crucial bit of evidence that the proton is made out of quarks. And for some reason, they move around freely when seen at short distances. But on the other hand, they don't come out. So that was a puzzle, paradox. It required theoretical understanding. And I became obsessed with that problem. Lesson number 7. Obsession can be a good thing. Einstein once said, I'm not the most intelligent person in the world. Everybody thinks Einstein was so smart and intelligent. He was, of course, very smart and very intelligent. But he said, my distinguishing characteristic is that I'm like a bulldog. When I get interested in a problem I regard as fundamental, I sink my teeth into it like a bulldog, and I hold on to it until I find a solution. Now, in the end, 5 years after these experiments, we came up with an explanation. And it has to do, I don't have time to explain to you, although I would take another 10 minutes, but I don't have the time, how this works. But it has to do, remarkably, with the properties of the vacuum. Now, you might think the vacuum, which is boring because the vacuum is just nothing. But in quantum mechanics, that's not the case. In quantum theory, the vacuum is full of fluctuating fields and particle-antiparticle pairs popping into existence, and the vacuum is a very complicated medium. It's like a piece of metal, it can be quite complicated, or silicon, or it's a substance in of itself, even though all matter has been taken out. Because of the nature of quantum mechanics, everything fluctuates in any state, including the ground state or the vacuum. And I'm going to show you a picture of what the vacuum looks like at the scale. It looks different at different scales. If I look at the vacuum here in this room, no structure at all. I need a much better microscope that can see distances of a millionth of a centimeter, nano scale. Then I see something like this. This is what the vacuum looks like. This is a calculation with the theory of the nuclear force, PCD, quantum coherence, that we came up with. But this is what the vacuum looks like at the scale of the nucleon. So this is about how big a proton is. A proton is like this. At that scale, the vacuum has, you see, looks like a complicated medium with fluctuating fields. These are fields of force between the quarks, like the electromagnetic field, except the source of this field are those colors. Instead of just one charge of electromagnetism, there are three charges, which we call those colors. And this is what the vacuum looks like. And this medium is complicated and has strange properties. And what it does, it mediates the force between these quarks. So in electromagnetism, the force lines spread out, and the force law is an inverse square law. Gravity and electromagnetism both have inverse square law. Force falls off like 1 over the distance squared. But in the presence of the vacuum, those force lines, flux lines we say, are squeezed by the vacuum to form a tube. And this is what it looks like. I'll show you a better picture in a moment. That phenomena of the generalization of electromagnetism to a situation where there are three kinds of charges, that's called the Yang-Mills theory or non-abelian gauge theory. Is what we call asymptotic freedom, because it has two implications. First of all, it tells you that when you bring the quarks together at very short distances, the force gets weaker and weaker. And asymptotically, as you bring them to the same point, the force vanishes and the quarks move freely. And that could explain, perhaps, the experiments at Stanford. But conversely, it means that when you pull the quarks apart, the force gets stronger. Totally counterintuitive. Bigger force farther away, and that's what prevents you from taking the quarks out of the nucleus. This is a picture using the real theory that we developed, based on computer calculations of what happens if you pull two quarks apart. And you can see the flux lines being squeezed to this tube. And that led us to this theory that had this phenomena called quantum chromodynamics, the theory of quarks bound together by this field whose source is color and whose property is this asymptotic freedom. Now, if you're a theorist, it's very satisfactory to come up with a new idea that might explain observed phenomena. But then you have to wait for nature to be the judge. You have to wait for experimental proof. The only judge in the end of a theoretical framework, a theory or a model, is that it makes predictions that can be tested in order to show that the theory is wrong. That you can do. You can always show that the theory is wrong if your theory is powerful enough. Make precise predictions that can be compared with experiment. You can never tell that a theory is correct, any theory. You can only say that it hasn't been disproved by observation. And in the case of QCD, it took some time for this theory to confront precision tests. So this is 1989, which is 16 years after the theory was proposed, and this is the prediction of asymptotic freedom. This is the measure on this axis of the strength. How strong is the nuclear force? And this is distance. So if we go here, we're going to shorter distance, and the strength should decrease. But it's a very slow decrease. This is the prediction of the theory, the black line, and these are experimental results. And as you see, well, the theory works, fits the data, but so does a straight line. You know, the data is not that good. There are error bars. So should you take this as a verification or a confirmation of QCD even after 16 years? Well, some of us could, but not the British Academy. This is what it looks like 6 years ago. This is now the prediction of the theory, and this is how it agrees with experiment. And this is not one experiment. There are literally hundreds of experiments that are used to confront this prediction and many, many hundreds of other predictions with the data. Oh, sorry, this is the straight line no longer is a good fit, for sure. But, you know, for a theorist, that's how you really get assurance that your theory might be correct. You make a prediction, you ask your experimental friends to check it, they go out, 16 years later they check it. But even more satisfactory for me was, if we have a theory of the nuclear force, if the proton is made out of quarks held together by this strange force that's weak at short distances and strong at large distances, we should be able to calculate anything we want about nuclei, and today we can. In particular, we can calculate your mass. Now, I'm sure you might have wondered sometime, what is the origin of your mass, of your weight? Now, of course, you might say it's the food I ate yesterday. So where does your mass come from? Well, you're made out of atoms that make up the molecules that they're made out of, right? So presumably your mass comes from the mass